welcome back my dear friends. A very good morning, good afternoon, good evening to all the participants, students who are taking this NPTEL MOOC course, the title of which is Application of Forecasting, Regression and Time Series Models. And my good name is Raghunandan Sengupta from the IME department at IIT Kanpur. So, as you can recollect, there are three broad areas for this course, which is for 30 hours, 60 lectures, each lecture being for half an hour. And the three broad topics are areas are forecasting, regression and time series analysis. We are the second part in the fag end, which is to do with regression models. This is week 10, lecture number 49. What is the coverage? Coverage is again continuing different examples. If you can recollect, starting from the 46th, 47th, 48th, we have considered about 7 different examples, and in this one we will consider another 2, and if time permits consider the third one also on this. That means, we will be in a position to consider 10 different models, and again I am saying the models are being discussed based on a simulated set of data. No programming is used, only Excel sheet is there, where you can have different scenarios being generated for the how the nonlinear regression models look like, based on 3 important facts. Number 1, how the parameters can be changed, which is the main focus. Number 2 is that what is the seed value from where you are starting x, what is the increment values of x, how you can change, because that would also have an effect on how the graph will pan out. And the third one, which is the main focus, but I still kept it as a idea which you can change, is basically what type of error we can have. The errors can be of 3 types, which is in the very simplistic sense. A uniform discrete between -a to +a, we can change -a to +a so that you can have more variance, less variance. The second one is basically normal distribution with 0 mean and sigma square as the variability, and third one is the t distribution with n degrees of freedom being that as n degrees of freedom increases, it becomes standard normal deviate with 0 mean and 1 standard deviation. The first one is the logistic one, and again as I mentioned here, and which we have done in the last 3 lectures in when we considered another 7 models. The idea was we will show the graphs in the PPT slide, but the detailed analysis that how you can change the parameters, how you can change the seed value, how you can change the delta x value of increments, how you can have an overall effect on how the errors look like, all are there in the Excel sheet side by side. So, let me come to the Excel sheet. So, we are going to discuss the logistic regression. So, let us take the logistic regression graph first. This is the one. So, we will move the Michaelis-Menten model. Here on to the left. Polynomial we will discuss later on. So, we will come back to that. Wait, let me handle it. Yes. Yes, and the graph related to this one. The logistic response, it is written as logistic response with the logistic model. Here it is, the graph along with the data set and the simulation, how it can be done in the same way. Yes, now it should be clear. Let me move a little bit onto this. So, as usual, we have the logistic response for all of them, we are just highlighting. So, there is theta 1, theta 2, theta 3. If we go to the graph, y is equal to theta 1, which is in the numerator, divided by 1 plus theta 2 exponential theta 3 x plus epsilon obviously. Theta 1, theta 2, theta 3 are following. Theta 1, theta 2 are the unknown parameters and theta 3 is the exponential factor for x. Error terms, as I said, I will repeat it, can be simple case 3 types. We are using the uniform discrete, but which I mentioned, as the Excel sheet is shared with you, play with the data, play with the the error terms, and you can have a whole gamut, whole universe of different type of curves, which will give you a much better understanding about nonlinear regression models. So, the first part, here you consider theta 1 as 200, theta 2 as 3, theta 3 as minus 0.15, 1.5. This is 200, this I will consider as 3 and this I will consider minus 1.5. So, this is the curve. So, I need to basically change the errors. Obviously, I can change the delta values of x and x values also. Let me change the delta. Yes, with x starting value as 2, let me make it 1.5. 1.75, let me check. If I take it as 2, yes. So, this is almost replicating what we see in the Excel sheet and the PPT file. So, if I have a look at the errors, so the errors are given as the case where they are being generated from the uniform discrete case. Now, one thing is important, once we finish all the discussion about the logistic response and the polynomial one, I will spare some few extra minutes or extra seconds to understand the error term, how we are simulating. This is just for interest, we will come back to that. So, rather than doing it for each model, I thought I will cover it at the end. So, the seed value for x is 2, delta values of x is 0.1, as usual theta 1 as mentioned is 200, theta 2 is 3, theta 3 is minus 1.5. As the graph is shown in the PPT, exactly the same type is being replicated and simulated in the Excel sheet. So, it makes sense. One important thing, if you remember in one of the distribution as we were discussing, we mentioned that what are the actual values of theta 1, theta 2 in the asymptotic sense. Here also it is important. If you consider the values of y, the asymptotic values of y, if you see in the column A V, which I am highlighting now, the asymptotic value of y is 200, which is exactly equal to the value of theta 1 based on which you are starting. So, let us check what the statement which I am making, that theta 1 is the asymptotic sense the value of y as x goes to infinity. Let us change theta to say for example 100. Obviously, the graph will change, but the main focus is now the asymptotic value of y. So, also this becomes asymptotic. If you see it, that asymptotic sense in the blue best fit line, obviously the errors would be there. So, if I check the asymptotic value of y, it is 100, which means theta 1 is the asymptotic sense the value of y as x tends to infinity. Now, that is the statement which I am making, the asymptotic sense is very easily discernible from the equation. How? See, if you see this in this equation, the value of e to the power theta x and x tending to infinity, it becomes a very large value, and if you take x as negative in that fact, so it will become a very large value, and then when it is taken here with a negative value, the denominator will always tend to 1. In the sense theta 2 is there, but it will become 1, because theta 2 would also be neglected as it becomes e to the power a very large negative value. So, in the long run x tending to infinity y value will slowly turn out to be theta 1, which I have been mentioning based on the fact that theta 1 in one case I take as 200, in another case I take as 100. Now, another thing, this value of theta 3 is negative. What happens if I take the value, and also check in the graph, what happens with if I take the value of theta 3 as positive? Let us take as same value, let us go back 200 for theta 1, then theta 2 as minus 2, and the value of let us take is plus 2. So, it will be easy, because we are trying to showcase the effect of theta 3. So, in one case theta 3 is minus 1.5, let us take it as plus. So, in this case the value of theta 1 was 200, that in the asymptotic sense would not be the value of y, because there is a positive theta 3. Positive theta 3 means in the denominator the value will increase, become infinite. So, whatever the value of theta 1, y will tend to be 0. So, at an asymptotic sense, in case if theta 3 is positive, in the long run y value will become 0 and the curve will go asymptotically as shown here. So, that would give you a much better feel that what is the behavior of the nonlinear regression curve for different values of theta 1, theta 2, theta 3, which is in this case the logistic response model. Now, another important thing, if I increase theta 3 to a very high value of negative, then the rate of convergence of y to the asymptotic sense to the theta 1 value would be much faster. So, let us check minus 3. So, if I take the value of minus, now do not look at the red points, I am only concentrating on the asymptotic sense and how fast y goes to theta 1. So, here you see the values at, so we start at x as 2 and by 4.6, which is by the 27th count y is 200. So, let us check that if that continues to be true as theta 3 is made more negative, let me make it minus 30. Very interestingly, you see as theta 3 becomes more and more negative, the asymptotic sense the value of y becoming the value of theta 1 would be instantaneous, because the denominator part which you have 1 plus that concept, because if you see in the model 1 plus that. So, this part which I am just highlighting would very quickly become 0. So, for any value of x immediately it becomes 0. So, y will tend to theta 1 immediately. As we make theta 3 less and less negative, say for example, I take it minus 0.1. So, in that case the value of y tending to theta 1 will be much later for larger values of x. Here it has not become, because even by the 124th value it is still 135. So, we need to check. So, you can basically compare. Okay. Now, coming back to the case of when we have the logistic response for 20, 10, minus 1. So, 20, 10, minus 1. So, if we see the curve with the errors have to be decreased a little bit to get the same replica of the data set as we had for as we see in the PPT slide. So, let me decrease the error. So, if you remember, this is the point which I am mentioning, we can play along with the starting value of x, incremental value of x, theta 1, theta 2, theta 3 of the parameters, the error terms, how they can be modeled. So, basically have a holistic viewpoint about how the models can be viewed. So, let me make it at twice. So, now you see the curve is more or less closer to what you are seeing in the PPT slide. So, in the case when theta 3 is 1, 200 is theta 1 and theta 2 is 3. Here theta 3 is 1, obviously asymptotically y will become 0 as shown in this PPT slide, and is will be reflected very soon in the Excel sheet. So, this is 200, theta 2 I am taking as 3, theta as 1. So, it is asymptotically becomes 0 as shown in the just simulated Excel sheet as well as in the PPT slide. The last one is for the case when you have theta 1 as 50, theta 1 as 50, theta 2 as minus 2 and theta 3 as 1. Now, what is interesting is the fact that in this case for a value of theta 3 positive, but it is overwhelming fact that how the curve will shape up and asymptotically go to 0 in the long run is now being dictated by theta 2 value, because it is negative. If I come back to the PPT slide, that will make sense, because here what we have is the values of theta 2 being positive and negative will dictate from which direction the y value asymptotically becomes 0. So, theta 2 being negative and positive would basically showcase that, and we have seen that in the discussions what we are doing in the last few minutes for the logistic response model. Now, when we come to the polynomial model, we are taking theta 1 plus theta 2 x plus theta 3 x square plus theta 4 x cube with an error term. Theta 1, theta 2, theta 3, theta 4 are the unknown parameter. Error terms as we know can be uniform discrete between minus a to plus a, uniform normal distribution with 0 mean and sigma square as the error, and t distribution with n degrees of freedom. So, let us go one by one in the graph. So, again I showcase this using the simulated data, and this is the polynomial one. Polynomial one, all the graphs are here. So, I remove the logistic response model to the left. So, they are stacked one after the other for ease of access for all of you. Let me check. Yes, this is the polynomial, right. So, there is no confusion here. This is the polynomial one here. One minute. Much better. Yes. So, now it is done. So, the polynomial one equation is for the first case minus 6 theta 1 theta 2 minus 0.3 theta 3 is minus 0.1 and theta this should be theta 4, my apologies, should be theta 4 is 0. So, this should be theta 4 also. So, if I have this value for the first case theta 1 as 5 done, theta 2 as minus 2 done, then theta 3 as 0.05 done, theta 4 being 0.001. So, this is the graph which you have, and this is exactly the replica which you are seeing here. So, it is a very nice way of trying to handle the polynomial equation with different values. So, it dips down and then increases. So, it is nothing to do, I am not talking about minimum value, maximum value, but it gives you that depending on what type of data which you have, you can simulate that. Now, the question for in the last starting from the 46th lecture, 46, 47, 48, this is the 49th one. So, half an hour is 2 hours. You may be thinking why I did not use any actual data, because trying to get an actual data with very small set of data points is the only feasibility, and trying to basically replicate that very small data set for this huge set of 9 to 10 different models is difficult. So, I took a different way of tackling the problem, that yes, you should know the regression models, nonlinear regression models. Yes, you should be aware that how the parameters affect the shape of this nonlinear regression model. Plus, I also thought that the seed value, the starting value of x, how the errors can be modeled would give you much more in-depth knowledge about the nonlinear regression, different type of curves. And obviously, once you understand that, trying to replicate with a real data set would be much more easier, because having an understanding about the simulation and having a good feel about how these 3 sets are under control, you will be able to appreciate the utilization in the real data set much better. In the second case, we have theta 1 as -5, then theta 2 as 0.5, then we have theta 3 as 0.01, and you have theta 4 as 0.0002. So, this is the curve which we have for these 4 different combinations of theta. So, that is also because here it does not decrease and increase, it is increasing. The more on emphasis on the right hand side where the increase happens. Now, interestingly, the curve totally changes for different combinations, and what are the combinations? Theta 1 4. So, let us make it theta 1 4, then let us take it theta 2 as 0.2, take theta 3 as 0.05, and let us take as theta 3 as minus 0.0002. See, the curve changes, which means as the value of theta 4 is negative, because it has an overwhelming effect later on and dips down. So, in the initial graph it went down, then went up. Here it first goes up and then comes down. So, with the same exact equation with different values of theta 1, theta 2, you are panning out different types of nonlinear regression models, which may fit different sets of data points. So, and in the last one, you have this is right portion when it is going down, theta 1 is minus 6, theta 2 is minus 0.3, theta 3 is minus 0.1, and this is 0. Oops, oh no, my mistake, this would be 0. Yes. So, minus 6, minus 0.3, minus 0.1, and theta 4 is 0. So, you have the graph as shown here. Now, again I am repeating before coming to the errors, playing with the theta 1, theta 2, theta 3 values, you may take time, but it will pan out different ways, as I showed here. Some of the graph is first decreasing, then increasing, depending on theta 1, theta 2, theta 3. In another case, it increases, then decreases. So, how you want to basically view which parameters have more pronounced effect on the non-regression regression curves can also be found out here. Here, if you remember, for at least the polynomial regression, I did not do anything with the error. Error was as it is. So, I was more interested to understand how the theta 1, theta 2, theta 3 and theta 4 values pan out. Also, I did not change the starting value of x, seed value of x, and also I did not change the delta values of x. Again, because the main emphasis was how the parameters affect the shape and the way the curve behaves. Now, if I consider the error term, so I will show you something here. This would be shared if possible in this case. So, I will consider uniform discrete, this is the normal. I will not be able to do the T 1 here, because that may not be possible considering the Excel sheet. So, let me do it for random number being generated between 0 and 1 minus 0.5. What do I get? This is important. So, I will make a set of say for no, this is not the place, it has to shift a little bit onto the right. I will make some some 518 data points, which is good enough. And here I have norm SINV, norm inverse. This will be rand, because random number will generate between 0 and 1. So, I have done. Now, you check. So, I have generated a uniform discrete and a normal standard deviation. So, let us check the mean and variance, which is important. So, let me do it a little bit more, like rather than 518, how about 1000 if possible, and check. So, there are 849 data points. So, let me increase it. About 980. So, it should be done. Now, if I consider the mean value, so average, sorry, it should be average. And this is average here. So, average value both for them comes to be almost 0. Interesting. Now, for this uniform random, what is the A and B value? So, I will take it as mean here. So, this is I will write as mean for for the normal distribution. This is minimum, this is maximum, that will give me A and B. So, if I take minimum, if I take maximum, very interestingly, this uniform distribution, which was of the formula random minus 0.5 generates a random variable between minus 0.5 to plus 0.5 with a mean value of 0. Interesting. What is the variance? So, this is the minimum, maximum and the variance. So, I will mark them with yellow color. I will mark them here also with, say for example, orange color, just for differentiation. So, this is orange is for normal, yellow is for uniform discrete. I will spend some extra minutes here today. Now, I need to find out the variance. So, the variance is var p for the population constraint. I find out the total variance. So, it is about 0.08. Now, if I do the same thing for minimum, same thing for maximum, same thing, no, var, yes. Very interestingly, for the case, if you see, the mean values are almost same. Obviously, if you simulate more, it will be. So, they are almost 0, in the sense one is 0.00158, 0.031. People may comment, no, it is not 0, but if you simulate time and again with a huge data set, it will slowly turn out to be 0. That can be guaranteed. Another thing I am guaranteeing is the minimum value, maximum value are minus 0.5 and plus 0.5 based on the random number generation, and here something interesting will come up. The minimum value for the normal and the maximum value for the normal are as value minus 3.5 plus 3.4. They are very huge values onto the right or the left for the standard normal. Obviously, actually they are in the long run they will be minus infinity plus infinity. And this is variance. Variance is, we know it is 1 because the standard normal deviate 1, and that is also matching. Now, interestingly, we will keep the mean value for the the uniform discrete as 0, but the variability I will increase. So, let us do the simulation. So, I will take this as multiplied by 3 and then check what is the minimum and maximum value for done. Now, you see the minimum value and maximum value are between minus 1.5 and plus 1.5. Mean value remains same 0, but variability has increased, which means that we are able to incorporate such error terms in the modeling part. Similarly, for the standard normal deviation, I am using simple Excel inbuilt function. You can have different type of normal distributions, in the sense 0 mean with other variability. So, those also can be replicated in this model. This I thought I will spend time, because if you see it hear it carefully, exactly the same type of simulation for the errors have been done in all the different type of 9 models. First 2, then 3 and then 2 plus 2, that means. So, we have completed 46th, 47th, 48th, 49th, all was dedicated to nonlinear regression models, and main emphasis is rather than the theory, how the simulation can be done to have an understanding how the parameters are affected by how the parameters affect the nonlinear regression models, they shape and how they behave. And obviously, the starting value, the seed value, the error terms were also discussed. So, with this I will end this 49th lecture and continue the last lecture, which is the 50th one for the 10th week. The last lecture would be for nonlinear regression, and then we will start for the last big part of this course, which will be the time series analysis. Thank you very much and have a nice day.